Differentiability. Recall that a one-variable function y equal to f of x is differentiable at x equal to a if the derivative f prime of a exists, which means that the graph can be approximated near x equal to a by a line, the tangent line. So a two-variable function f of x and y is differentiable at a and b if it's locally linear. That is, if you basically zoom in around point P, what you see is closer and closer to a plane. So that is, the graph can be approximately near point A and B by a linear function, the tangent plane. Again, that zooming in closer and closer gets you more and more close to a plane. Differentiability and non-differentiability, example 2. So let's function be defined by the piecewise as x squared times y over the square root of x squared plus y squared if x and y is not equal to 0, 0, and equal to 0 to be x and y equal to 0 and 0. If you remember from 15.2, this part, the limit of x squared times y over square root of x squared plus y squared as x and y approached 0 was of undeterminate form, and we solved and we got that the limit would have been 0. But that one has a hole, so we have to define that separately. So this is not an elementary function, but look at how it actually around 0.00. It's not elementary, right? So see if it's flattening down as x and y. So in the beginning, I had x and y between -1 and 1, then x and y between -1/10 and 1/10, and then x and y between -100 and 100, and so I'm zooming in as I go, and it flattens down around that point. So let's look at this graph in the GeoGebra also. So here's the graph of the function. It's an elementary function. It's not elementary at 0, 0, 0. So, now if I basically try to zoom in, this is zooming in, it's flattening down. I'm zooming in, and you see that it's flattening it around 0 and 0. I should zoom in right at 0, 0. See, it's getting flatter and flatter as we go. So this function is actually differentiable at 0 and 0, even though it's not an elementary function at 0 and 0. And the graph resembles a plane. Now let's give another non-elementary function at 0 and 0. So again, differentiability and non-differentiability, example 3. This time, function is equal to x squared times y divided by x squared plus y squared when x and y is not 0, 0, and it's equal to 0 when x and y is equal to 0. So when x and y is between between -5 and 5, that means that you are basically graphing a big chunk of the function. Looks like this. Zoom in between -1 and 1, still that, between -1/10 and 100, and this one is not differentiable because it still is not flattening down completely. And let's go to the link. So here in GeoGebra, I'm trying to zoom in at this point. So I just zoom in and I zoom in and I zoom in, and still has the crease going on forever and ever. And so it's not flattening down. So that's the basic definition. Not every non-elementary function is not differentiable, and some of them are differentiable, some of them aren't. This one, for example, is not differentiable, the other one was. But looking at when the derivatives exist, you're sort of looking for non-differentiable, for non-elementary functions to be non-differentiable. And so now, algebraic definition of differentiability. Let's first define differentiability, because we haven't defined differentiability. We're just telling you how it looks like we did in calculus of single variable. We show differentiability meant what it meant. There wasn't supposed to be corners or going to infinities and that sort of things, or discontinuity didn't count. Well, same things are apply here also visually, but there's also the limit definition in here as well. And so we know that tangent plane, if it exists, has this equation, right? But if I can write the tangent plane, it doesn't mean that the function is differentiable. What does it mean the function is differentiable? Here's the definition. The function is differentiable at a and b if the linear function L sub a and b is a better and better approximation to the graph of f of x as x and y approaches x, a, and b. So here's the linear function, and that's and so the difference between the linear function, that's the z equal to, that's the equation of the plane. If the difference between z and x and y as over the difference between the magnitude of the difference between x and y and a and b, this is the magnitude of the difference between point x and y and a and b. If the limit of that as x and y approaches a and b equal to 0, then the function is differentiable. However, nobody wants you to check this. Unlike what we asked you in calculus 1, in calculus 3, we're not asking you to check the differentiability using this limit definition. But it's interesting to see that the complexity changes when you go from calculus 1 to calculus 3 in defining the limit definition of the derivative. Right? And it requires a little bit more, basically. So what do we have any good tool to check for differentiability? Yes, we do. Calculus of one variables. If f prime exists, then it's different. The function is differentiable. Calculus of multivariable. If f of x and y is differentiable, then f sub x and f sub y exist. But the other way around is not enough, basically. Criterion for differentiability: if both partial derivative f of x and f of y are continuous at a and b, then f of x and y is differentiable at a and b. The other way was okay without continuity. If f of x and y is differentiable, both f sub x of a and b and f sub y of x a and b exist. But for function to be differentiable, f sub x and f sub y are supposed to be continuous, not only exist but continuous at a and b. So in particular, all elementary functions such as polynomial, rational functions, trig, log, exponential functions are differentiable on their domain, and be worry about piecewise defined functions. Those are non-elementary. Example 4, differentiability versus partial derivatives. Example 4, let f of x and y be x squared y over x squared plus y squared for x and y not equal to 0 and 0, and 0 for x and y equal to 0 and 0. And so let's see if, this is actually the example that we just did, example 3, and we figured out from the graph of the function that it's not differentiable. To completely show that it's not differentiable, we have to go back and use this limit definition and show it's not differentiable. But we also can look at the graph as we did in calculus 1 and say, well, this is not differentiable. Now, what's differentiable, and something to notice is that actually the partials for this function are defined, but they're not continuous. And so how do we find the partial for this function? Finding partials for this function, first of all, if you're finding partials at points other than 0, 0, you just take the derivative with respect to x and with respect to y. If you're finding partials at 0, that's a little different story. You have to write the definition of the derivative by plugging in x equal to 0 and writing the definition of derivative as if the input variable is y, or by plugging in y equal to 0 and finding the definition of the derivative as x is equal to 0. And here's the thing. So f sub x at 0, 0 is limit of f of x and 0 minus f of 0, 0 over x, and f partial respect to y at 0, 0 is the limit as y approaches 0 of f of 0 and y minus f 0, 0 over y. In both cases, you end up with 0. So the partials at 0 are 0. But the partials anywhere else, you don't need to use the definition of the derivative. And it's just that the point that it's not elementary function, and that's the 0, 0. Now, it turns out the partial at any point, any other point other than 0, 0, partial respect to y is going to be x squared over times x squared minus y squared over x squared plus y squared to power 2. And this limit, the limit of this partial as x and y approaches 0, 0 does not even exist. Not only not equal to value of the partials at this value of the partial over there, but also it doesn't even exist. So the partials are not continuous. That doesn't, and so that you can see that the function is not differentiable and one of the partials not continuous.